This is a single still photograph. Now watch, a machine brings it to life, and not one frame of this motion was ever filmed. But none of it was filmed. Every new frame was imagined, conjured out of pure noise. So, how does a machine bring a photo to life? So what is motion to a machine? Take 2 frames of a video, a moment and the next, and measure how far each little piece of the picture moved between them. That's a motion field, a tiny arrow at every point. And this isn't drawn, it's measured, straight from the footage. Watch where the arrows gather, on the parts that actually moved, the kicking leg, the arm, while the still parts and the background stay quiet. Now stretch a grid over the frame, and bend it along that field. The mesh warps exactly where the motion is, the limb pulls, the rest holds still. And that's one way to make a picture move. Copy a field like this and bend the picture along it. But a machine that wants to move a picture doesn't track every single pixel. That's far too much. Instead, it finds just a handful of points that matter. It runs a small network, a detector, on the first frame. Out the bottom come heat maps, a bright blob wherever a joint probably is. Take the peak of each blob, and you have a key point, a shoulder, an elbow, a knee, landed right on the body. Then the exact same detector, the same weights, on the second frame. The blobs shift because the body has moved. Now there are key points in both frames, and the difference between them, that's the motion. Line the 2 up, the same detector, 2 frames, a skeleton in each. Subtract one from the other, and you get how each key point moved, a direction for everyone. And here's the crucial part. That direction can only exist because there were 2 frames. A single frozen photo has no motion in it. The second frame is what gives every arrow its direction. But a few arrows can't move a whole picture, so a second network, a U-net, takes that sparse motion and fills in the gaps, predicting a movement for every pixel. Out comes the dense field, drawn here as a deformation grid, and that grid is exactly what bends the picture into its next moment. But wait, nobody ever told this machine where a shoulder or a knee is, so how did it learn to find them? Here's the trick. From the source frame, the whole pipeline predicts what the next frame should look like. But we already have the real next frame. It's right there in the video. That's the answer. So compare the guess to the real thing. How far off was it? That gap is the error. And that error flows backward through every stage. The warp, the U-net, the key points, the detector, nudging each one to do a little better. Do that millions of times across millions of frames, and the key points settle onto real joints, the predictions sharpen, and nobody ever labelled a single one. The next frame was always the answer key. Copying has a limit. It can only reproduce a motion that already exists. It needs a driving video to imitate. To invent new motion from a photo alone takes something more. It's the method behind today's video generators. And it isn't a different idea, it's the same move. Predict a field and follow it. Only now, the field lives over the space of every possible video. Motion transfer copied. This one imagines. In the last act, a machine moved a photo by copying motion from a video that already moved. But what if there's no video to copy from? Just one still picture? Can a machine imagine the motion from nothing? Here's a single photo, a neutral stance. What happens next? She could kick, she could punch, she could just stand up. There isn't one right answer. And that's the first surprise. The machine doesn't give one answer. It begins each future from a different patch of random noise, a different seed. Each seed fills a whole clip's worth of frames, 25 of them, every frame pure static, for now. Then it clears the noise away, step by step, and out of each seed a different future emerges. Same girl, same starting pose, but change the seed and you change the future. One photo doesn't hide one video, it hides a whole tree of them. One thing we glossed over. Real video generators don't diffuse pixels. A whole video is simply too big. So first, an autoencoder, a VAE, squeezes each frame down into a small latent, a tiny grid of numbers that still holds the picture. And all the diffusion, all the noising and all the denoising happens down here, inside that compressed space. Far cheaper and far faster. Only at the very end does the VAE's decoder turn the finished latent back into pixels. And that compressed space is a learned version of our space of all videos, which is why the VAE is still everywhere in modern generators. So how does it imagine even one of these? Let's follow a single future, the kick, and open it up. Here are its frames, still mostly noise, the video being born, and here's our one photo. The first thing the machine does is put a copy of that photo onto every single frame. So each one knows who it's supposed to be drawing. Underneath, that's a simple, exact operation. A frame isn't red, green, blue here. It's a compressed latent, 4 channels of noise. The photo is compressed the same way, into its own 4 channels. And you just stack them together, the frames 4, the photos 4, 8 channels going in. That's all conditioning really is, the photo riding along with every frame. Those 8 channels feed the workhorse of the whole thing, a UNet. In goes the tensor, 72 by 128, 8 channels deep. And it does what you saw in the first film, it squeezes the picture down. Each step halves the height and width, while the channels grow, trading resolution for understanding. Then it builds it back up to full size, with shortcuts across so it never forgets the fine detail. And out the far side comes something the size of a frame, but it isn't the frame, hold that thought. Because the real magic is what happens inside those blocks. It's attention, the same idea from the first film, doing 2 jobs here. The first, looking within a single frame. Every position in the frame becomes 3 vectors, a query, a key, and a value. Each position, as a query, scores itself against every other position and takes a weighted blend of their values. Watch a few of them. As a spot attends up on the picture, its row of scores lights up down below. That's spatial attention. Every position sharing information with every other, all 576 at once. It's how a single frame becomes coherent. And then the second job, the one that makes video hard, the very same machinery but across time. Take one position and follow it across all the frames. Now each frame is the query, the key, the value. And each frame attends to all the others along the time axis, its value becoming a blend of what came before and after. That's temporal attention. It's the whole secret of consistency, why the leg stays the same leg and the face the same face, frame after frame, instead of flickering into someone new every moment. So, condition on the photo, squeeze through the UNet, attend across space and time. And what finally comes out the end? Not the video, a guess of the noise, the machine's best estimate of exactly what static is corrupting each frame right now. So you subtract a little of that noise away and the frames get a touch cleaner. Then feed it back in and do the whole thing again and again, about 25 times. And slowly, out of the static, a clean, imagined clip appears. We've watched diffusion generate, but how does its denoiser ever learn to predict noise? The trick is stranger than you'd guess. Take that frame, pick a random amount of noise, a random time t, and add it in. Now you have a half-noisy frame and you know exactly how much noise went in. Feed that noisy frame and the level t into the network. It's one job, guess the noise that was added. The loss is simple. How wrong was the guess? The noise you added is the answer key. No labels, no critic. Just spot the noise. And because t is random every single step, one network learns every level, from a faint haze all the way to pure static. Compare that to everything we've seen. Motion transfer reconstructed the next frame. VQ-GAN reconstructed the image with a critic. Diffusion does neither. It corrupts, then predicts the corruption. And that's why it builds a picture one small step at a time, instead of all at once. Now, why go to all this trouble when copying was so much simpler? Here's why. Take the same photo through both engines. One warps it, one generates it from scratch, and ask for things that need pixels. The photo doesn't contain a new expression, the hidden side of a face, a camera pushing in, something entering the scene. Copying can't. It only rearranges what's already there, and those pixels were never there to move. But imagining can. It isn't trapped by the photo, it just dreams the missing pixels up. That's the trade the whole story turns on, bounded or free. So here's the same photo brought to life two ways. Copy the motion from a video that already moves, faithful but bounded, and it needs that driving video. Or imagine it from noise, free to invent, but it had to learn, from millions of clips, how to stay consistent. Each buys you something, and each makes you pay for it. Same goal, bring a photo to life. But look at what each one really does. Copying takes a single motion from a video that already moves. Imagining samples from a whole distribution of futures it learned. Two completely different minds. Let's tie all of this together. Picture the space of every possible video, where a single point is one entire clip. The real ones aren't scattered at random, they cluster by kind. Here, the space of realistic kung fu videos. Here, cats, dogs, basketball, and nature. Everything else is noise. So here is the question, how does a machine get from noise all the way to here? The answer has three names, but it is really one move. Predict a field and follow it. The first is flow matching. It learns a velocity at every point, a whole field of little arrows, branching and climbing toward each cluster of real videos. Drop a seed of noise and simply follow that field. The sample rides the arrows, and noise becomes a real video. Here, a kung fu clip. One field, learned once, follow it and noise turns into video. The second is score matching, diffusion. Instead of one field, it learns the shape of the data at every level of noise. At high noise, it is a single broad blur. As the noise falls, it sharpens, step by step, into well-separated modes, the clusters of real videos. On each slice, the score points toward higher density, toward the nearest mode. So start in the noise and follow the score, a noisy walk that gradually denoises the sample, until it condenses onto the kung fu mode, a real video. The third is the older cousin, a normalizing flow. It starts from a simple spherical Gaussian, easy to sample from. Then a stack of invertible layers bends the space, each one exactly 1-to-1, nothing lost, and the points cluster. Follow a single point. The same map carries it from prior to data, and it runs backward exactly. By the last layer, the density matches the data, a real kung fu video. But what actually computes these fields? Behind each one is just a small neural network. For flow matching, the network predicts a velocity, a few big steps. For score and diffusion, it predicts the denoising direction, a noisy walk of many small steps. And for the normalizing flow, the network is the stack of invertible maps, warping the whole neighborhood straight onto the data. 3 little networks, and here is the beautiful part, we can actually train them. Let's make that real. Here are 2 tiny networks, each just a little MLP that takes a 2D point and a time and hands back a 2D arrow. And we actually trained them. We gave both the very same thing to learn, a spiral. And each one learned a real field of arrows pointing in toward that spiral. This is the trained network's actual output, not a drawing. Now start from random noise and follow the field to the data. Watch the difference. Diffusion wanders in through a haze of noise, about 100 little steps. Flow matching glides in almost straight, in just a few. Same destination, 2 temperaments. And here's the twist. Diffusion's deterministic version is itself a flow. That is exactly why they're cousins. There's an older cousin in this family that works in a completely different way. Start simple, pure Gaussian noise and a plain square grid. A normalizing flow learns one invertible function that bends that entire space. warping the grid until it fits the data. And because it's invertible, it runs backwards exactly. Run it the other way, and the spiral flattens right back into noise. There's no field to follow here, and no 100 steps to integrate, just a single, reversible map, exact in both directions. So step back. There are 3 ways to turn noise into data. 2 of them learn a field you follow, diffusion and flow. The third learns a map you invert. Same goal, reach 3 different ways. Before we finish, look back at Act 1. That warp field, carrying every pixel to its next position, that was a flow. And that deformation grid, carrying the source to the pose and exactly back, an invertible map. The seeds were there all along. Diffusion just set them loose over the space of every possible video. So, how does a machine bring a photo to life? It predicts a field, a set of arrows saying which way to move, and it follows them from noise to a real video. Copy 1 motion or imagine 1,000. It's the same move, just in a different space. That's how a machine brings a photo to life.